Welcome to another lecture on fluid mechanics. So we will continue our discussion on viscosity of different fluids. So we have defined viscosity or dynamic viscosity in the previous lecture, and also we have just seen what do you mean by a Newtonian fluid or a non-Newtonian fluid, Newton's law of viscosity, etc. So we will discuss more on viscosity. So for this, let us discuss on rheology of fluids. Rheology or rheological behavior of fluids we will discuss. So what is meant by rheology exactly? So it is a science of shear deformation of fluids. So we have already seen when we apply a shear force, what happens? A shear stress is being developed in solid mechanics. So we have seen fluid friction or viscosity in fluids. The shear stress is developed due to the effect of viscosity. So the development of this shear stress is different for different fluids, or in other words, different fluids are having different viscosity. So if you are applying a same shear force, what about the deformation of different fluids? So that is exactly defined by the term rheology of fluids or rheological behavior of fluids, or we will put it in another way. That means there is a velocity profile, as we have seen in the previous lecture. There is a velocity profile from solid body towards the free surface of the liquid due to the effect of viscosity. So the shear stress developed due to this velocity gradient. So we will study that. So that is different for different fluids. That means a study or science that deals with the shear deformation. If you compare butter with kerosene, the deformation under the action of an applied shear stress is different. So tau equal to mu du by dy whole raised to n. So that is a general equation. If n equal to 1, that becomes Newtonian. That is, tau is linearly varying with respect to du by dy. Newtonian fluid. Mu is the dynamic viscosity as per Newton's law of viscosity. Now with respect to this equation, we will discuss the rheological properties of different fluids. That means we are in fact categorizing fluids into different categories with respect to their rheological behavior or its behavior, property or characteristics against a shear force. Newtonian, as we have already seen, the best examples are kerosene and water, n equal to 1. That is linear variation between shear stress tau and du by dy. Okay. Next one is non-Newtonian. Any fluid that does not obey the Newton's law of viscosity is non-Newtonian. That means n is taking a value other than 1. Examples: slurries, polymer solutions, blood, etc. Binigam plastics, tau equal to mu c plus mu du by dy. So it is also behaving somewhat like Newtonian, but after a certain quantity of stress. You see this? If tau, that is shear stress, exceeds c value, that is a particular value of stress, tau is equal to mu du by dy. That means a minimum amount of stress is required for such fluids to behave in a Newtonian way. Example is sewage sludge. If you take fluids such as clays and drilling mud, they are behaving differently. They are non-Newtonian in nature after the application of certain amount of stress, that is c here. So these are known as thixotropic. So thixotropic and Binigam plastics are more or less behaving identically. The only difference is one is behaving Newtonian, other one is non-Newtonian after a minimum stress is applied, that is C. Next one is ideal fluids. Ideal fluids means what? They are incompressible, constant density, then inviscid, no viscosity. If there is no viscosity, when it is flowing, it does not induce any shear stress. So they are ideal fluids. Now if n is less than 1, that means slope of t versus tau versus mu du by dy, that is slope of tau shear stress versus du by dy graph. We will discuss the graph in the next slide. That is, a graph is drawn between shear stress and velocity gradient. That means between tau and du by dy. Is n equal to 1, that slope is 45 degrees, then that becomes a Newtonian fluid. If n is less than 1, slope is less, than that of Newtonian, then it is called pseudoplastics. We will discuss later. Examples: paper pulp and rubber paints. If n is greater than 1, higher slope than Newtonian, on the tau versus du by dy graph, it is called dilatant fluid. Examples are butter, printing, etc. So if you just see the different fluids which are hinted here, like water, kerosene, slurry, sewage, butter, printing paint, paper pulps, etc., these are having different characteristics when subjected to a shear force. So that is what exactly meant by the rheology of fluids. And now, as I have already just hinted, we are drawing a graph between shear stress on y-axis and velocity gradient on x-axis. You see this? So velocity gradient, ideal fluid is this, that means no shear stress is 0. Then on y-axis you have elastic solid. So irrespective of the amount of shear stress applied, no change in velocity gradient. It's a solid, known as elastic solid. So between these two regimes you have different graphs. You can draw this Newtonian, that is the blue line, the dilatant one, that is the green one, non-Newtonian, any fluids which is having a value of n not equal to 1, then it's real plastic, as we have seen in the previous diagram. Then this ideal plastics and thixotropic. You see this is a minimum value of stress C. Okay, so once you apply this minimum value of stress C, the ideal plastics behave in a Newtonian way, whereas the thixotropics behave in a non-Newtonian way. This minimum stress is required, that we have seen in the previous equation, tau equal to C plus du by dy whole raised to n. Okay, so this is a picture or image of a rubber paint. This is a polymeric solution. This is a mud picture. So why these are shown here is that you can see and sense the viscosities of different fluids like rubber paint, polymeric solutions, mud, etc. So this is about the rheological behavior of different fluids. And now we have already discussed about the velocity distribution of different layers of the fluids, or when a viscous fluid, when it is flowing through an open channel or through a pipe, we have seen that velocity is varying from 0 to maximum if it is an open channel flow, and if it is a closed pipe flow, velocity is 0 for the layer that is sticking the solid boundary, and it is maximum at the center. So this is, as I told in the previous lecture, this is exactly due to the phenomenon of viscosity. This velocity distribution is happening. So also we have discussed the no slip condition and all. So 0 at the solid boundary and increases away from the solid boundary. So it has got different velocity profiles. If you consider pipe flow, it may be parabolic or parabolic, that logarithmic. The velocity profile may be parabolic, as we have shown here, 0 here, maximum at the center. It may be logarithmic, again 0 here, maximum at the center. So this is for laminar flow, this is for turbulent flow. That depends later in this section. And now we will define another property, that is kinematic viscosity. So we have seen dynamic viscosity mu, that divided by mass density will give you kinematic viscosity. So how can we deduce units for kinematic viscosity? Unit of dynamic viscosity, that is Newton second per meter square, divided by unit of mass density, kilogram per meter cube. That will give you Newton second meter per kilogram, and Newton unit of force, that is kilogram meter per second square, because F equal to m into A. So kilogram meter second square divided by kilogram second meter. So meter square per second. So the SI unit of kinematic viscosity is meter square per second. So we know that SI unit of dynamic viscosity is Newton second per meter square, or Newton per meter square second, or Pascal second. So we always express this kinematic viscosity as well as dynamic viscosity in terms of their commercial units. Commercial unit of kinematic viscosity is 1 stock. So you should know the conversion from stock to SI unit, that is 1 stock equal to 10 raised to minus 4 meter square per second. You should study that. Then similarly the conversion from commercial unit of dynamic viscosity. Commercial unit of dynamic viscosity is poise. So conversion is like this: 1 poise equal to 0.1 Newton second per meter square. So in many numerals you are given the values of dynamic viscosity as well as kinematic viscosity in terms of their commercial units. So sometimes if you are given the dynamic viscosity of a fluid is 20 centipoise, that means what? 20 into 10 raised to minus 2 poise. Centi means 1 by 100. So 20 into 10 raised to minus 2 poise, that is 0.2 poise. That means what? 0.2 poise means 0.2 into 0.1 SI unit, that is 0.02 Newton second per meter square. So you should know this conversion, that is very important. Okay, so this table, in fact, it shows a comparison between the different fluids in terms of their viscosity values as well as kinematic viscosity values. So first column is centipoise, as I have already said, commercial unit. Similarly, second column is in centistocks, that is again the commercial unit of kinematic viscosity, and SSU, that is Seibold universal seconds or Seibold seconds universal, that is another unit of expressing the viscous behavior of fluids. You see this on the scale, water is taken as 1 centipoise. So you can compare the viscosities of other fluids with respect to water. If you take cream, it is 16.5 times more viscous than water. If you take SAE 30 oil, that is 352 times more viscous than water, because centipoise, in terms of centipoise, the viscosity 352. As we move down, the viscosity increase. If you take SAE 70 oil, it is having a centipoise viscosity 17,640. So what I am telling is that this table is shown for a comparative analysis of the viscosities of various fluids that we come across in engineering practice. Okay, so in the table you can see some of the engine oils here: SAE 10, SAE 50, SAE 70, etc. So generally engine oils are expressed as SAE W30, SAE W40, SAE 5W30, etc. So what does it mean actually? As a mechanical engineering student, you should know what does it represent. You see this. This is commercial engine oil valvoline. This is for module. See on the top of this you can see SAE 5W30. Here you see SAE 0W40. So what does this number as well as this character W represents? So first number represents its viscosity representation in winter. That means the 5W, 5 is the viscosity representation in winter seasons. Similarly, 30, that is the second number, represents its viscosity representation in normal conditions, normal temperature and pressure. So that means what? During winter, if you take SAE 5W30, its viscosity is only 5 in one of the units. Similarly, for normal atmospheric conditions, it is 30. That means what? It varies with respect to temperature. Which one? The dynamic viscosity varies with respect to temperature. Then how it varies and why it varies, that is very important. So we conclude like this, that is, viscosity of any fluid varies with temperature. You see, then how about this variation? We'll discuss more on this. For liquids, it decreases with temperature. That means as the temperature is increased, the dynamic viscosity of liquids decreases, whereas for gases the behavior is in the opposite direction. That means for gases the viscosity increases with temperature. Okay, so that you should understand this different behavior for liquids as well as gases with the temperature for the property viscosity. And now you will see some of the commonly found examples. Honey can be made to flow readily when heated. That means if you heat honey, it will flow at a easier pace. Engine oils thickens appreciably on cold days. That means during winter seasons, the engine oils are having more viscosity than its normal temperature conditions. That means what? That means you see this as during cold days. That means as the temperature decreases, engine oil's viscosity increases. Similarly, when temperature increases for honey, that is also a liquid, its viscosity reduces. That is why it is flowing easily or readily. That means temperature and viscosity are two very important factors with respect to the rheological behavior of fluids, especially liquids. Then let us see why this happens, why this variation with the temperature happens for viscosity. There are two contributing factors to viscosity as far as one of the models presented. One is due to the force of cohesion, and the other one is due to the force of intermolecular momentum exchange. You see this, what is cohesion? Cohesion, as you see, it is the force of attraction between like molecules. If you take if it is a oil liquid, the attractive force, that is the binding force between oil molecules at its structure, is known as cohesion. What is intermolecular momentum exchange? That means exchange of momentum between the particles or the molecules. Why it is happening? Liquids which are having more entropy, or particles are ready to move at a faster pace or vigorously than in solids. While they move, they collide with similar particles, they exchange their energy, they exchange their momentum. So this intermolecular momentum exchange between particles of the fluids are also contributing to viscosity. So these two factors, how these are affecting, let us see. As the temperature increases, this cohesive force decreases. We'll see that. Similarly, as the temperature increases, the intermolecular momentum exchange increases. How this is happening? You see this as this representation. It's a pictorial representation of why or what is happening as temperature is increasing for cohesive force. Cohesive force means the binding force, the molecular force of attraction. As the temperature increases, the kinetic energy of the fluids at the structure increases. It gives more energy for the molecules. So more energy for the molecules means that binding force is getting weakened up. So cohesive force reduces. When the cohesive force is reduced, that is force of binding reduces what? It is free to move. That means it leads to increase in viscosity for liquids. Okay. Then this is how this molecular momentum exchange is depending upon the increase in temperature. Again, as the temperature increases, what happens? The molecules are getting more kinetic energy due to the heat energy gained by the structure. Then more kinetic energy, they are free to move anywhere. That means momentum exchange with other particles increases. So that leads to viscosity. So what happens? There are two contradicting factors. As the temperature increases, cohesion increases, cohesion decreases, that leads to decrease in viscosity. Whereas as the temperature increases, intermolecular momentum exchange also increases, that leads to increase in viscosity. So what is the end effect? For liquids, cohesion is more predominant. For gases, intermolecular momentum exchange is more predominant. So things are clear. Okay. For liquids, cohesion is more predominant. For gases, molecular momentum exchange is more predominant. So the net effect is decrease in viscosity of liquids when heated, because cohesion is more predominant than intermolecular momentum exchange in liquids. That decreases. So as temperature is increased, the viscosity reduces for liquids, whereas gases behaves in the other way. That means gases, the intermolecular force of attraction, that is van der Waals force, is getting weakened up. So that increases, give rise to a more better value for molecular momentum exchange, and hence increase in T, that is temperature, leads to increase in viscosity for gases. That means gases and liquids behave differently with the temperature as far as the viscosity property is concerned. So the commonly found gas, that is commonly cited gas in engineering practice applications, is air. You see the property of viscosity of air with the temperature. You can see on x-axis it is 25 degrees Celsius. Then the dynamic viscosity is expressed in micropascal second. Pascal second, as I already told, that is the SI unit of viscosity. Micropascal second, that is Pascal second to 10 raised to minus 6. It is almost 18.5 at 25 degrees Celsius. So when the temperature is increased to 100 degrees Celsius, it is 21.5. So there is no corresponding hike, but there is a hike in value of viscosity of air with increase in temperature from 25 degrees Celsius to 100 degrees Celsius. You see one of the liquids, most cited liquid, that is water. Water at 25 degrees Celsius, it is having a viscosity of about 880 micropascal second. So when the temperature is increased to 100 degrees Celsius, viscosity drastically reduced to about 250, 260. So that means there is a significant reduction in viscosity with the temperature for water, generally for liquids. So why I have shown this is for to have a general idea about how the viscosity varies for air and water, and also you can see the corresponding numerical values. If you take 25 degrees Celsius, what is the viscosity of water, etc. Okay. So this is the end of this current video lecture, and now after this we will do some numerical problems also in the next lecture.